Alright, so the last video I uploaded was uploaded without any audio, so I figured I should probably re-record and just upload the new video, which is fine. I can redo it. Last time I wanted to talk about some physics stuff, kind of an application of calculus. I wanted to talk about a scenario where I take a ball and I throw it up in the air, and let's say I wanted to graph what happens to the height of the ball over time. So I'm just going to have the horizontal axis be time, represented in seconds, and the vertical axis to be in meters. So what happens when I throw a ball up in the air? So at 0 time, I haven't thrown the ball up in the air, so the ball is at 0. Let's say after 3 seconds, the ball is at 3 meters, and let's just say, I'm not exactly sure what time this is, but maybe at some point the ball is here, and the ball maybe was here. What would happen if I kept checking smaller and smaller incremental points? I would see a curve emerge, and the curve would be in the shape of a parabola. Basically, a parabola, what that means is that at some point where the ball reaches its peak, the curve going after is a mirror reflection of the curve of it going up. So it's basically saying that any object that's thrown up in the air, like a ball, will fall in the same amount of time that it took to get up to its highest point. We can write an equation to describe this curve. Since it's a parabola, we can say that the height is equal to some constant a times t squared plus another constant b times x. Now, the a and the b are constants. We don't know what they are, but they don't vary. The thing that varies in this case is time. So time is the variable. And what this equation is saying is, if you give me a time, and this should be a t. If you give me a time, I'll give you the height of the ball. But at the moment we don't know exactly what these values a and b are. But what we do know is these different points in time. So let's say at time 3, for example, the ball was 3 meters in height. So I can just plug in what I know and find the relationship between a and b. So I'm saying that the height was 3. When the height was 3 meters, the constant times the time, which was 3 seconds, and it's squared, so the t squared, so the time is squared, it's 3 squared, plus that constant times the time again. So what we see is 3 is being equal to 3 squared is 9. You have 9a plus 3 times b. So I'm going to put a box around that because I'll be using that equation in a second. Another point in time, let's say, let's look at time equals 2. Let's just say the height right here was, that looks to be about 2.5 meters. So I could put 2.5 for the height is equal to that constant a times the time squared. Well, the time at that point was 2, so we have 2 squared plus b times that time. Oops. Oh, that's strange. Okay. Hold on. Alright, I fixed that little glitch. I think I was just about to solve the second equation. So 2.5 is equal to 4 times a plus 2 times b. So I have 2 equations, 2 unknowns. That means there's only one solution to this this equation. These are called systems of equations. And the way that I'm going to solve them is by elimination. I'm going to solve for one of the unknowns, and plug that in to the second equation to get one equation with one unknown. So one thing I can do is I can multiply the entire equation right here by -2 over 3, and I'm going to rewrite it down here underneath this second equation. So if I do -2 times 3 is -6 divided by 3 is -2. So I have -2 is equal to -2 times 9 is -18 divided by 3 is -6. So you get -6a, and then -2 times 3 divided by 3 is just -2b. So what I can do now is add these two equations together. I get 2.5 minus 2 is 1/2. I get 4 minus 6 is -2. And 2 minus 2 is 0. I'm left with just this part of it, which tells me that a is equal to -1. Because if I divide both sides, sorry, not -1. If I divide both sides by -2, I get that a is equal to -1/4. But that's only half the problem, because I still need to solve for the unknown number b. So what I can do is I can plug a back in for either of these equations. I think I'll take the second equation because it looks a little bit more easier, but really I could plug a equals -1/4 into either equation. So in this case, -2 is equal to -6 times a, but a is equal to -1/4, and then minus 2b at the end. And what I can do now is just multiplied through, I get 6/4 minus 2b. If I put 2b on the other side and minus 2 on the other side, I get 2b is equal to 6/4 plus 2, which is the same as saying 8/4. And you get 14/4, and b dividing by 2, you get 14/8, which is 7/4. Alright, so I just checked my math, and it's correct. So what I do is I take a and b and I plug them back into that height equation. I'll rewrite it down here. The height is equal to -1/4 times squared plus 7/4 times time. So if we just look at that, just inspecting those values, if the time is if the time is 0, then it's 0 plus 0 and the height is 0. So that point at the beginning checks out. It's not a particularly interesting point, but it does check out. Another point we should probably check is at time equals 3, what happens. In this case, the height will be equal to -1/4 time squared. Time was 3, which squaring that you get 9, and then plus 7/4 times the time, which is 3. I'll get rid of that. So what we're left with is the height is equal to -9/4 plus 21/4, and that equals, let's see, 16/4, which hold on, no, that's not right. 12/4, not 16/4, 12/4, which equals 3. So what we had said is when the time equals 3, the height was at 3. So that's what this equation shows, is when you set time equal to 3, the height is equal to 3. You can also check that for any of the other points on the graph, but that is the equation that describes that ball as I throw it up in the air. The next thing I was going to talk about, or I will talk about in the video, is velocity. So this graph plots the ball's vertical position in space over time, and what we see is the velocity of the ball over time changes. So right after I release the ball, it's got the maximum speed, because as time goes on, that velocity gets smaller. So like this first arrow is maybe where is maybe equal to high, a velocity of 2 meters per second, let's say, and then after a certain amount of time, maybe it's only 1.5 meters per second, and so over here at the peak, the velocity is 0. It doesn't want to go any higher or any lower at that point in time. So its velocity is 0 at the peak, and then as you start going back down, let's draw one more there. On the opposite side, there's a velocity equal to the negative of the velocity on the mirror side. So again, it's maybe a little bit like that, and then wherever it lands, it's going to land at the same speed that it had when it started. So what we can do is we can plot the velocity over time to see how fast it was going as time moves on. And what you can kind of glean from the arrows is that it starts out going pretty fast, but then over time it drops to 0, and then in fact it even goes negative for some time after that until it hits the ground. So again, time in seconds and velocity in meters per second. And what this is actually a straight line, and so it's called a linear equation. And the equation looks something like this: the velocity equals, so I'm going to do something sneaky here, and I'm going to do 2 times a number t plus a constant. Again, 2 times, and I could put a letter here, c to equal, and as a matter of fact, let me do that. First, I'll just write it as this: the velocity equals some constant times time plus another constant. So the thing that you can do is, at this point, you can solve it the same way I solved this equation up here, by putting in the known points, and then solving for the unknown constants. Or you can you can know that the height is, or I should say the velocity is equal to the derivative of the height with respect to time. So it's dh dt, or you could call it h prime. There's a couple other ways, but basically what this is saying is that velocity is the derivative of the height with respect to time. The velocity in the vertical direction is the derivative of the height in the vertical direction over time. So in one of my other videos, what I did was I talked about taking the derivative with respect to x of a constant times x, and we found that you can write it as that constant times the derivative with respect to x of x, and the derivative of x to the n is equal to n x to the n minus 1. So that being said, we can apply that to this first portion here. So v is equal to a constant times a variable, the derivative of a constant times a variable. So just like I did over here, I'm going to factor out the constant, and I'm going to write d by dt of t plus d by dt of the constant b. So let me just check my notes here. The derivative of a constant is equal to 0 because there's no hold on. Okay, let me back up a little bit because I made a mistake. So I was taking the derivative of this function right here, when in fact I should be taking the derivative of the height function. That's kind of why it was screwing me up. This is a way to describe this graph, and like I said, you can plug in numbers and solve for this equation, but the way that I want to solve it is by taking the derivative of the height equation with respect to time. The height equation was negative 1/4 t squared plus 7/4 t. So what I want to do is I want to take the derivative with respect to time of this whole formula. So on the left side, I get dh dt, which by definition is velocity. And if I take the derivative of a constant times t squared, if I take the derivative, let me just write it over here, x to the n is equal to n times x to the n minus 1. So in this case, it's negative 1/4 times 2 times t to the first power, which is just t. And then I'm taking the derivative of a constant times the variable, which in this case is just 7/4. So what I find is the velocity equals this I'm calling c. This negative 1/4 is actually a, comes from here actually. So that's why I was doing 2 times a, because this is 2a plus b, and then a is negative 1/4, b is 7/4. So the a and the b kind of followed from the height equation, followed into the velocity equation. We got 2 times negative 1/4, which is negative half a plus 7/4. So this is the equation for this graph, the graph of the velocity. And finally, I want to talk about acceleration. So acceleration is, we have time in second, and we have acceleration in meters per second squared. So if we look at this graph, this kind of tells us, this helps us see what the acceleration is. What we see in this graph is that every time time moves by, let's say, 1 second, the velocity will decrease in this instance by a half. So you go down 1 and you go across a half, and you get to the next point, and you go down 1 and you go across a half, or the ratio between going down and going over is -1/4, or -1/2, sorry. This should be, so it's -1/2. So what the acceleration is doing, let's say this is 0 and this is -1/2, it's a constant acceleration. It's and its value is -1/2. One way we can see that is to say that acceleration is the derivative of the velocity over change in time. And we can just solve the same way we did previously. We have a constant times t, taking the derivative with respect to t, that's just -1/2, and the derivative of a constant is 0 because there's no change. It's always a constant, so the change in time is 0. So all said and done, the acceleration is equal to -1/2 meters per second squared. So just to reiterate, we started with a function h and we know the equation of a parabola is that the derivative of h in terms of time is equal to velocity is equal to 2a times t plus b, and the derivative of the velocity with respect to time is I'll use uppercase A for acceleration, is equal to 2a. So this is the relationship between position, velocity, and acceleration.